SHA-2 is a set of cryptographic hash functions designed by the NSA. SHA stands for Secure Hash Algorithm. Cryptographic hash functions are mathematical operations run on digital data, by comparing the computed hash to a known and expected hash value. A person can determine the data's integrity. For example, computing the hash of a downloaded file and comparing the result to a previously published hash result can show whether the download has been modified or tampered with. A key aspect of cryptographic hash functions is their collision resistance. Nobody should be able to find two different input values that result in the same hash output. SHA-2 includes significant changes from its predecessor, SHA-1. The SHA-2 family consists of 6 hash functions with digests that are 224, 256, 384 or 512 bits. SHA-224, SHA-256, SHA-384, SHA-512, SHA-512 224, SHA-512 256. SHA-256 and SHA-512 are novel hash functions computed with 32-bit and 64-bit words, respectively. They use different shift amounts and additive constants, but their structures are otherwise virtually identical, differing only in the number of rounds. SHA-224 and SHA-384 are simply truncated versions of the first two, computed with different initial values. SHA-512 224 and SHA-512 256 are also truncated versions of SHA-512, but the initial values are generated using the method described in FIPS Pub 180-4. SHA-2 was published in 2001 by the NIST as a U.S. federal standard. The SHA-2 family of algorithms are patented in US 6,829,355. The United States has released the patent under a royalty-free license. In 2005, an algorithm emerged for finding SHA-1 collisions in about 2,000 times fewer steps than was previously thought possible. Although no example of a SHA-1 collision has been published yet, the security margin left by SHA-1 is weaker than intended, and its use is therefore no longer recommended for applications that depend on collision resistance, such as digital signatures. Although SHA-2 bears some similarity to the SHA-1 algorithm, these attacks have not been successfully extended to SHA-2. Currently, the best public attacks break pre-image resistance for 52 rounds of SHA-256 or 57 rounds of SHA-512, and collision resistance for 46 rounds of SHA-256, as shown in the Cryptanalysis and Validation section below. Hash standard. With the publication of FIPS Pub 180-2, NIST added 3 additional hash functions in the SHA family. The algorithms are collectively known as SHA-2, named after their digest lengths. SHA-256, SHA-384, and SHA-512. The algorithms were first published in 2001 in the draft FIPS Pub 180-2, at which time public review and comments were accepted. In August 2002, FIPS Pub 180-2 became the new secure hash standard, replacing FIPS Pub 180-1, which was released in April 1995. The updated standard included the original SHA-1 algorithm, with updated technical notation consistent with that describing the inner workings of the SHA-2 family. In February 2004, a change notice was published for FIPS Pub 180-2, specifying an additional variant, SHA-224, defined to match the key length of 2 key triple DES. In October 2008, the standard was updated in FIPS Pub 180-3, including SHA-224 from the change notice. but otherwise making no fundamental changes to the standard. The primary motivation for updating the standard was relocating security information about the hash algorithms and recommendations for their use to special publications 800-107 and 800-57. Detailed test data and example message digests were also removed from the standard, and provided as separate documents. In January 2011, NIST published SP800-131A, which specified a move from the current minimum security of 80 bits allowable for federal government use until the end of 2013, with 112-bit security being the minimum requirement current thereafter, and the recommended security level from the publication date. In March 2012, the standard was updated in FIPS Pub 180-4, adding the hash functions SHA-512-224 and SHA-512-256, and describing a method for generating initial values for truncated versions of SHA-512. Additionally, a restriction on padding the input data prior to hash calculation was removed, allowing hash data to be calculated simultaneously with content generation, such as a real-time video or audio feed. Padding the final data block must still occur prior to hash output. In July 2012, NIST revised SP800-57, which provides guidance for cryptographic key management. The publication disallows creation of digital signatures with a hash security lower than 112 bits after 2013. The previous revision from 2007 specified the cutoff to be the end of 2010. In August 2012, NIST revised SP800-107 in the same manner. The NIST hash function competition selected a new hash function, SHA-3, in 2012. The SHA-3 algorithm is not derived from SHA-2 applications. The SHA-2 hash function is implemented in some widely used security applications and protocols, including TLS and SSL, PGP, SSH, MIME, and IPsec. SHA-256 is used as part of the process of authenticating Debian GNU Linux software packages, and in the DKIM message signing standard, SHA-512 is part of a system to authenticate archival video from the International Criminal Tribunal of the Rwandan Genocide. SHA-256 and SHA-512 are proposed for use in DNS-SEC. Unix and Linux vendors are moving to using 256 and 512-bit SHA-2 for secure password hashing. Several cryptocurrencies like Bitcoin use SHA-256 for verifying transactions and calculating proof of work or proof of stake. The rise of ASIC SHA-2 accelerator chips has led to the use of script-based proof-of-work schemes. SHA-1 and SHA-2 are the secure hash algorithms required by law for use in certain U.S. FIPS Pub 180-1 also encouraged adoption and use of SHA-1 by private and commercial organizations. SHA-1 is being retired for most government users, the U.S. National Institute of Standards and Technology says. Federal agencies should stop using SHA-1 for applications that require collision resistance as soon as practical, and must use the SHA-2 family of hash functions for these applications after 2010. NIST's directive that U.S. government agencies must stop uses of SHA-1 after 2010 was hoped to accelerate migration away from SHA-1. The SHA-2 functions were not quickly adopted, despite better security than SHA-1. Reasons might include lack of support for SHA-2 on systems running Windows XP SP2 or older, and a lack of perceived urgency since SHA-1 collisions have not yet been found. The Google Chrome team announced a plan to make their web browser gradually stop honoring SHA-1-dependent TLS certificates over a period from late 2014 and early 2015. Cryptanalysis and validation. For a hash function for which L is the number of bits in the message digest, Finding a message that corresponds to a given message digest can always be done using a brute force search in 2L evaluations. This is called a pre-image attack and may or may not be practical depending on L and the particular computing environment. The second criterion, finding two different messages that produce the same message digest, known as a collision, requires on average only 2 evaluations using a birthday attack. Some of the applications that use cryptographic hashes, such as password storage, are only minimally affected by a collision attack. Constructing a password that works for a given account requires a pre-image attack, as well as access to the hash of the original password, which may or may not be trivial. Reversing password encryption is not made possible by the attacks. In the case of document signing, an attacker could not simply fake a signature from an existing document. The attacker would have to produce a pair of documents, one innocuous and one damaging, and get the private key holder to sign the innocuous document. There are practical circumstances in which this is possible. Until the end of 2008, it was possible to create forged SSL certificates using an MD5 collision. Increased interest in cryptographic hash analysis during the SHA-3 competition produced several new attacks on the SHA-2 family, the best of which are given in the table below. Only the collision attacks are of practical complexity. None of the attacks extend to the full round hash function. At FSC 2012, researchers at Sony gave a presentation suggesting pseudo-collision attacks could be extended to 52 rounds on SHA-256 and 57 rounds on SHA-512 by building upon the bi-click pseudo-pre-image attack. Official validation implementations of all FIPS-approved security functions can be officially validated through the CMVP program, jointly run by the National Institute of Standards and Technology and the Communications Security Establishment. For informal verification, a package to generate a high number of test vectors is made available for download on the NIST site. The resulting verification, however, does not replace the formal CMVP validation, which is required by law for certain applications. As of December 2013 update, there are over 1,300 validated implementations of SHA-256 and over 900 of SHA-512, with only 5 of them being capable of handling messages with a length in bits not a multiple of 8 while supporting both variants. Examples of SHA-2 variants: hash values of empty string, SHA-224 0xD14A028C2A3A2BC9476102 BB2882344C415A2B01F828 each 62 AC5B3E42 FSHA-256 0xC3B0C44298 FC1C149AFBF4C8996 FB92427A41E4649 B934 California 495991 B7852 B855 SHA-384 0x38 B060A751 AC 96384 Candelas 9327 EB1 B1 E36A21 FDB 71114 B07434 C0 CC7 BF63 F6E1.274 EDB for 76 F65 FBD 51 AD2 F14898 B95 BSHA 512 0x CF83E1357 EEFB8 BDF1542850D66D80007 D620E4050 B5715 DC83F4A921 D36CE9 CE47 D0 D13C5 D85 F2B0 FF8318 D2877 EC2 F63 B931 BD47417 A81 A538327 AF927 DA3E SHA-512 224 0x 6 ed 0 DDO2806 FA89E25 D060C19 D3 AC86 CAB 87 D6A0 DDDO5C333 B84 F4 SHA-512 256 0xC 672 B8D1 F56 ed 28 tab 87 C3622 C5114 BDD3 AD 7 B8 F9737498 D0 C01 ECEF 0967A. Even a small change in the message will result in a mostly different hash, due to the avalanche effect. For example, adding a period to the end of the sentence changes 111 out of 224 bits in the hash. SHA-224 0 by 730 E109 BD7 A8 A32 B1 CB 9 D9 A09 AA 2325 D24305 87 D DBC 0 C38 BAD 911525 SHA-224 0 by 619 CBA 88 5826E9 B8 C519 C0 A5 C68 F4 FB 653 E8 A3 D8 AA04 BB2 C8 Candelis 40 Pseudocode for the SHA-256 algorithm follows. Note the great increase in mixing between bits of the W1663 words compared to SHA-1. Note 1. All variables of 32-bit unsigned integers and addition is calculated modulo 232. Note 2. For each round, there is one round constant k, I, and one entry in the message schedule array w, I, 0, I63. Note 3. The compression function uses 8 working variables, A through H. Note 4. Big Endian convention is used when expressing the constants in this pseudocode, and when parsing message block data from bytes to words. For example, the first word of the input message, ABC, after padding is 0 by 61,626,380. Initialize hash values. H0 equals 0x6A09 E667 H1 equals 0xBB67A85 H2 equals 0 by 3C6F372 H3 equals 0xA54 FF53A H4 equals 0x510 E527 FH5 equals 0x9 BO568 CH6 equals 0 by 1 F83 D9 AB H7 equals 0 by 5 B0 Candelis 19. Initialize array of round constants. K 0 63 equals 0 by 428 A2 F98 0 by 71,374,491 0 x B5C 0 FBCF 0 x E9 B5 DBA5 0 x 3956 C25B 0 by 59 F111 F1 0 by 9 923 F82A4, 0 SHA-1C5 Ed5, 0 XD807 AA98, 0 X12835 B01, 0 by 243,185 B. 0 by 550 C7 DC3, 0 by 72 B5 D74, 0 by 80 Deb1 Fe, 0 by 9 BDC06 A7, 0 XC19 BF 174, 0 XE49 B69 C1, 0 XEF BE 4786, 0 by 0 FC19 DC6, 0 by 240 California 1 CC, 0 by 2 D92 C6F, 0 by 4 A7484A, 0 by 5 CB0A9 DC, 0 by 76 F988 DAR, 0 by 983 E5152, 0 XA831 C66D, 0 XB00327 C8, 0 XBF 597 FC7, 0 XC6E00 BF3, 0 XD5 A79147, 0 X06 California 6351, 0 by 14,292,967, 0 by 27 B70A85, 0 by 2E1B2138, 0 by 4D2C6 DFC, 0 by 53,380 D13, 0 by 650 A7354, 0 by 766 A0 AB, 0 X81 C2 C92E, 0 by 92,722 C85, 0 XA2 BFE8A1, 0 XA81 A664B, 0 XC24 B8B70, 0 XC76C51A3, 0 XD192E819, 0 XD6,990,624, 0 XF40E3585, 0 by 106 AA070, 0 by 19 A4C116, 0 X1E376 C08, 0 X2748774C, 0 by 34 B0 BCB5, 0 by 391 C0 CB3, 0 by 4 Ed8 AA4A, 0 by 5 B9 CCA4F, 0 by 682 E6FF3, 0 by 748 F82E, 0 X78 A5636F, 0 by 84 C87814, 0 X8 CC 70208, 0 by 90 BFAR, 0 XA 4506 CEB, 0 XBEF9 A3F7, 0 XC 67178 F2 pre-processing. Append the bit 1 to the message. Append k bits 0, where k is the minimum number greater than equals 0 such that the resulting message length is 448. Append length of message in bits as 64-bit big-endian integer. Process the message in successive 512-bit chunks. Break message into 512-bit chunks. For each chunk, create a 64-entry message schedule array W0, 63, a 32-bit words. Copy chunk into first 16 words W0, 15 of the message schedule array. Extend the first 16 words into the remaining 48 words W16, 63 of the message schedule array. For I from 16 to 63, S0 equals XOR XOR S1 equals XOR XOR W. I equals W. I16 plus S0 plus W. I7 plus S1. Initialize working variables to current hash value. Equals H0B equals H1C equals H2D equals H3E equals H4F equals H5G equals H6H equals H7. Compression function main loop. For I from 0 to 63, S1 equals XOR XOR CH equals XOR and G. Temp 1 equals H plus S1 plus CH plus K I plus W. I S0 equals XOR XOR Marge equals XOR XOR. Temp 2 equals S0 plus Marge H equals G. G equals FF equals E equals D plus temp 1 D equals CC equals BB equals AA equals temp 1 plus temp 2. Add the compressed chunk to the current hash value. H0 equals H0 plus AH1 equals H1 plus BH2 equals H2 plus CH3 equals H3 plus DH4 equals H4 plus EH5 equals H5 plus FH6 equals H6 plus GH7 equals H7 plus H. Produce the final hash value. Digest equals hash equals H0 append H1 append H2 append H3 append H4 append H5 append H6 append H7. The computation of the CH and Marge values can be optimized the same way as described for SHA-1. SHA-224 is identical to SHA-256, except that the initial hash values H0 through H7 are different, and the output is constructed by omitting H7. SHA-224 initial hash values H07 equals 0xC1059 ed8 0x367 Candelas 507 0 by 3070 dd17 0xF70E 5939 0xFFCOOB31 0 by 68,581,511 0 by 64 F98 FA7 0xBE FA4 SHA-512 is identical in structure to SHA-256, but the message is broken into 10 24-bit chunks. The initial hash values and round constants are extended to 64 bits. There are 80 rounds instead of 64. The message schedule array W has 80 64-bit words instead of 64 32-bit words. To extend the message schedule array W, the loop is from 16 to 79 instead of from 16 to 63. The round constants are based on the first 80 primes to 409. The word size used for calculations is 64 bits long. The appended length of the message, in bits, is a 128-bit big-endian integer, and the shift and rotate amounts used are different. SHA-512 initial hash values H07 equals 0x6A09E667 F3BCC908 0xBB67A 8584 CAA73B 0 by 3C6 F372 Fe94 F82B 0xA54 FF53A5 F1D36 F1 0 by 510 E527 Fade 682 D1 0x9 B05688 C2B3 E6 C1F 0 by 1 F83 D9 ABF B41 BD6B 0 by 5 B0 Candelas 19137 E2179 SHA-512 round constants K079 equals 0 by 428 A2F98 D728 A22 0 by 7,137,449,123 F65 Candelas 0xB5C 0FBC FEC4 D3 B2F 0xe9B5 DBA 58,189 DBBC 0 by 3,956 C25 BF 348 B 538 0x59 F 111 F1 B 605 D019 0 by 923 F82 A4 AF 194 F9B 0 SHA-1 C5 Ed5 DUS 68118 0 XD 807 AA98 A3030242 0 by 12835 B01457006 FBE 0 by 243,185 B4 E4 B28C 0 by 550 C7 DC3 D5 FFB 4 E2 0 by 72 B5 D74 F27 B896 F 0 by 80 Deb1 Fe3 B1696 B1 0 by 9 BDC 06 A725 C71235 0xC19 BF 174 CF 692,694 0xe49 B69 C19 F14 Ad2 0xEF BE 4786384 F25 E3 0 by 0 FC19 DC 68 B8 Candelas 5 B5 0 by 240 California 1 CC 77 Act 9 C 65 0 by 2 to 92 C6 F592 B0275 0 by 4 A7484 AA6 each 6 E483 0 by 5 CB0A9 DCBD41 FBD4 0 by 76 F988 DAR 831,153 B5 0 by 983 E5 5152 E6060 FAB 0XA831 C6062 decibels 43,210 0XB00327 C898 FB213 F 0xBF 597 FC7 Beef 0E4 0xC6E00 BF33 DAR 88 FC2 0xD5 A79,147,930 AA725 0x06 California 6351 E003826 F 0 by 142,929,670 A0E6 E70 0 by 27 B70 A8546 D22 FFC 0 by 2 E1 B21385 C26 C926 0 by 4 D2 C60 FC5 AC42 AED 0 by 53,380 D139 D95 B3DF 0 by 650 A73548 BAF63 DEB 0 by 766 A0 AB3 C77 B2A8 0 by 81 C2 C92 E47 ED6 0x92722 C8514822353 B 0xa2 BFE8 A14 CF 10364 0xA81A664 BBC 423001, 0xC24B8B70D 0F89791, 0xC76C51A30654 B30, 0xD192E819D 6F5218, 0xD699062455565A910, 0xF40E358557712028, 0x106AA07032BBD1B8, 0x19A4C116B8D2D0C8, 0x1E376C0851441AB53, 0x2248774 CDF8EB99, 0x34B0BCB5E19B48A8, 0x391C0CB3C5C95A63, 0x4A8AA4A3418ACB, 0x5B9CCA4F7763E373, 0x682E6FF3D6B2B8A3, 0x748F82E5DEFB2FC, 0x78A5636F43172F60, 0x84C87814A1F0AB72, 0x8CC702081A6439EC, 0x90BFAR23631E28, 0xA4506 SEBDA82BDE9, 0xBEF9A3F7B2C67915, 0xC67178F2E3725532B, 0xCA273ECEA26619C, 0xD186B8C721C0C207, 0ZIADA7DD6CDE 0Eb1E, 0xF57D4F7F6Ed178, 0x06F067AA72176 FBA, 0x637DC5A2C898A6, 0x113F9804BEF90D, 0x1B710B35131C471B, 0x28 decibels 77F523047D84, 0x32CAAB7B40C72493, 0x3C9EBA 0A15C9BEBC, 0x431D67C49C100D4C, 0x4CC5D4BECB3E42B6, 0x599CFC657E2A, 0x5FCB6 Fab3AD6FAEC, 0x6C44198C4A47517, SHA-512 Summon Sigma S0 equals XOR1 equals XOR0 equals XOR1 equals XOR. SHA-384 is identical to SHA-512, except that the initial hash values H0 through H7 are different, and the output is constructed by omitting H6 and H7. SHA-384 initial hash values H07 equals 0xCBBB9D5DC1059 0x629A292A367 Candelas 507 0 by 9,159,015 A3070DD17 0 by 152 FECD8 F70E 5939 0 by 67,332,667 FFCOOB31 0 by 8 EB44 A 8,768,581,511 0xDB0C2E0D64F98 FA7 0 by 47 B5481 DBE FA4 FA4 SHA-512 T is identical to SHA-512 except that the initial hash values H0 through H7 are given by the SHA-512 TIV generation function. The output is constructed by truncating the concatenation of H0 through H7 at T bits. T equal to 384 is not allowed, instead SHA-384 should be used as specified, and T values 224 and 256 are especially mentioned as approved. The SHA-512 TIV generation function evaluates a modified SHA-512 on the ASCII string SHA-512 substituted with the decimal representation of T. The modified SHA-512 is the same as SHA-512 except its initial values H0 through H7 have each been XID with the hexadecimal constant 0xA5 A5 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 A5.